Hi friends, welcome to the channel Learning R is Fun. In the last two videos we have covered statistical tests, both parametric and non-parametric. In this video we will continue our discussion on statistical tests. Anova is an important test. And before going into Anova, that is Analysis of Variance test, we will just remind ourselves about the two sample t-test. Here in two samples, we test means of the populations. While doing so, we are either doing it in paired manner or in unconnected manner. That is, if the samples contain the same subjects after a certain treatment, before and after, then we use the paired samples. Paired samples are generally a preferred approach to reduce the number of items we need to get statistically significant results. But however, if the groups are independent, then we go for simple two-sample t-test or the independent sample test. Suppose if we have more than two groups, then how do you compare their means? That is where Anova comes in. Even though the name is Analysis of Variance, basically we do the comparison of the means. In particular, Anova tests are useful to check how far the sample means are different from each other and with how much variation is there within samples. That is, within groups and between groups. The variances is what we find out. In Anova again, we have one-way Anova and two-way Anova. In one-way Anova, we check the dependent variable, how it is varying based on the independent variable which is a factor. Here we use F distribution. But suppose we have more than one factor, then we go for two-way Anova. While doing one-way Anova, the number of observations need not be same in each group, whereas in two-way Anova, the number of observations in each group should be same. In two-way Anova, effect of two factors on the continuous dependent variable is what we find out. The interrelationship between the independent variables influence the values of the dependent variable is what is being studied. Say, to cite an example, we can classify the sales made by a firm first on the basis of sales by different salesmen. Second, by sales in different regions. John Tukey is a pioneer of data science. In fact, 50 years of data science, the paper he wrote is very relevant even today, and that link I have given, you can go through that. And suppose we have several groups and we are performing Anova, we will only know whether there is a difference or not. Suppose you want to find out how different they are, which of them are different, and you want to also find out that the difference which we are getting is really true, because in some cases, like when you do it a simple comparison using t-test, it may not really reflect the difference. It may give a difference, whereas in reality there will not be any difference. In such cases, Tukey's method of arriving at honest significant differences is very important. So these things we'll see in today's session. For today's session, the program has already been loaded. We'll have to load the package far away. So we'll do that first. First you have to do the installation, then you can load it. There is a data set coagulation. This coagulation is basically the ability of blood to freeze and the time in which the blood freezes for different animals. That is what has been captured in this data set. Let's ask R. What is this? Dataset comes from a study of blood coagulation times. 24 animals were randomly assigned to 4 different diets and the samples were taken in random order. So here we have got only 2 columns, coag, that is coagulation time in seconds, and diet, A, B, C, D, 4 types are there. Let's see the structure. So the diet is a factor, basically 4 levels, A, B, C, D, and coagulation times are given in seconds. Now let us make a plot to get an idea. Coagulation in terms of diet with the colors 2 to 5. So we have got 4 plots. You can see in respect of diet A, B and D, we see a balanced distribution of data. Only in case of C, the data is entirely concentrated between the median and the first quartile. We can also have a quantile distribution. Here 0% is 66 and then up to 50% data is also 68, 75% data is also 68 and 100% data is 71, which is considered as an outlier, and that is shown here. Now let us do the Anova, analysis of variance of coagulation with respect to diet. Based on diet, whether the coagulation times are getting different. So that will store in coag underscore AOV, and we can ask what is the summary. So R gives the summary, diet is significant. That's what we could see here. The probability is much less than 0.05. Therefore null hypothesis is rejected, then the effect is definitely assumed to be important. Okay. Now we know that the diet is important, but which diet is important out of the 4 diets and what is the effect? That you get from Tukey HSD. So we'll ask R, what is Tukey's HSD? Computing Tukey harness significant differences. Create a set of confidence intervals on the differences between the means of the levels of a factor with the specified family-wise probability of coverage. So they have given what are the arguments and how to go about. So generic function, John Tukey introduced intervals based on the range of sample means rather than the individual differences. That's why this becomes harnessed. Whereas in the independent sample test, sometimes you get a difference reported, but actually there will not be a difference. But that problem is overcome by harness significant difference. This is a post hoc test. Basically, after the Anova, if you find differences, then you do the post hoc test. And let us do this test now. We just give 2K HSD and then give the Anova object and then confidence level we specify and we get the results here. Here we can see the interactions very clearly given, PA, CA, DA, like that. All combinations are given. But when we look at these values reported by 2K HSD, we see no difference between A and D as well as B and C. So A and D, B and C. In these 2 cases, we find the adjusted p-values more than 0.05. That means we have to accept the null hypothesis that there is no significant difference. But in other cases, they are all less than 0.05. Therefore, we have to say we cannot accept the null hypothesis. Therefore, there is a difference. So B to A, C to A, D to B and D to C, there are differences. That's how we interpret. We can also do a plot of this. When we do this plot, it's easy to see here. We have to see whether 0 lies within that range. Now in the case of DC and DB, 0 is not lying. So therefore these are significant differences. In these 2 cases again, we find that 0 is not lying in these lines. Therefore these are significant. That's how we interpret this. So we can do much analysis by seeing the values, etc. But our aim is to just show you that how it is easy to do 1-way Anova or 2-way Anova using R. Now let's look at 2-way Anova. Here we'll use a example, rats. Rats data set basically is the effect of a poison and then the treatment. The survival time in tens of hours, that is time. Poison, there are 3 types of poisons, 1, 2 and 3. Treatment, there are 4 types of treatment, so A, B, C, D. So you have got unique combinations, 12 combinations. That is, you give a poison 1 and give a treatment A, B, C, D. For each of this poison, we can have 4 types of treatment. There is a 12 combinations here. Now, which of these combinations is effective? We need to know. So first let us see the data tabulated nicely using XTAB's contingent table. Now in fact, the method of tabulating the data using table and XTABs and various other methods is what we are going to see in the next video. So we have formed a nice contingent table here. So this is poison 1, 2 and 3, and these are the 4 types of treatment. Treatment A, treatment B, etc. So you administered poison 1 and you have given treatment A. What is the survival? Number of hours. That is the tabulation. Now the data is 48 rats were randomly assigned, both one of the 3 poisons and one of the 4 possible treatments. The experiments then measures their survival time in tens of hours. That means this is 16 hours. It is 16.5 hours. Okay. Now there can be so many models here. I have just given some examples. Time as a function of poison, time as a function of treat, time as a function of poison plus treat, or an interaction of poison and treat. That in this case it is poison, treat and then poison plus treat, all. So it can be anything. So, or we can use only factor A and then find out factor B only, and then we can find out like that. So before running the test, we can see one interaction plot. Let us ask, what is R? What is interaction plot in R? Plots the mean or the other summary of the response for 2-way combinations of factors, thereby illustrating possible interactions. Let us actually draw the plots and then we can get an idea. M of row, 1 row and 2 columns. There are 2 plots here. Here I am using interaction dot plot, poison, treat, time. Line width is 2, column is 1:4. When you use width, this data will be applied here. These variables will be found out from this data. Similarly, you can find out, instead of plotting poison x, poison as x and treatment as y, we can do reverse that and we will get one more plot. So let us execute these 3 statements. So I got 2 plots here. So we are seeing these lines here. These lines are not crossing each other. This is what we should see. If they are crossing somewhere, that means this interaction is important. Then we can go for actual Anova. Now summary of Anova here will take, and time as a function of poison interaction with the treat. So we'll use this. Let's find out the summary. Here when you use star, it means individually additive as well as the interaction. So we get a poison, we are getting what is called a significant result here, because p value is very less. Here also p value is very less, and an interaction term is there, poison and treat together. Here the value is not significant. Residual is basically what is not explained by these factors, that will be coming up in the residuals. So we see in this only poison and treat individually has got a significant effect. We can also see them in the, so since we have seen only additive terms are important, we'll use time as a function of poison plus treat and then find the Tukey. So here again we have got the probability values and we can interpret which of these combinations are important. Say for example here this null hypothesis is rejected here and here and here. We can say on these three places. Here this is more than 0.05, therefore null hypothesis has to be accepted. Here also it is to be accepted. Here also it is to be accepted. So in three cases, that is in the combinations of CB, DA and BA, these combinations, and here also we have got two combinations here. This is more than 0.05, therefore this is null hypothesis is accepted, therefore there is no difference, significant difference here, whereas 3.1 and 3.2, these are important. So people take decisions based on this kind of inputs which they get from Tukey HSD as a post hoc test. We have covered 1-way Anova with one factor and 2-way Anova with the two factors. And we have seen the complications involved, and we have also seen how to do a post hoc test, which is Tukey HSD. So in the next video, we will be covering the contingent table. We understand the contingent table is a summary of the data available in a specific format, and that contingent table, how it is used for certain statistical tests. Thanks for watching, and bye from me.